Hi, welcome back. We're in lecture 18 and the topic is repeated measures ANOVA. In the first segment, I just walked you through an overview of repeated measures ANOVA, highlighting sort of the pros and cons of adopting this kind of design. Now let's walk through a full example. Again, I'm going to use the working memory training example. I promise this is the last time I will use this example in this course. Definitely the last time. But it's an excellent example because when I first read that paper, I was very confused. I just assumed that they would have had the same people train 8 days, 12 days, 17, 19, and assess them at multiple points, do it longitudinally. Would have been much more powerful. And there have been people who've done that subsequently. So if you remember the original one, there were 4 different groups. There were 20 per group, so that gave 80 subjects. But now let's think of it as repeated measures. We only need 20 subjects. This exact experiment hasn't been done, but we simulated some data just to analyze and show here. So we simulated some data in R, and here are the results. We made it up just to mimic the results from the between groups design. But you'll notice one big difference here is we've plotted it as a line graph instead of a bar plot. And the reason for that is it's the same subjects across the 4 conditions. So it's sort of accustomed to use a line graph to demonstrate that the same people are measured longitudinally. That is, you're measuring growth within individuals, not across separate groups represented by separate bars. It's a little bit of a tedious point, but I think it's nice to illustrate that graphically and adhere to that standard. So there's one sort of quirky thing about R that I want to highlight right away. In almost any other software package, and it's just sort of a rule in data structures, is there's typically 1 row per person or per entity. So if you have your first subject, subject 1, and they were in these 4 conditions, we assessed their intelligence at these 4 time points, then we would have just 4 columns representing those assessments. That's just a common data structure format. Most software packages adhere to that. If you're doing a repeated measures ANOVA in R, however, they don't structure it that way. And a lot of people get frustrated when they first start to learn R because it's confusing how to do a repeated measures ANOVA. But you just have to structure your data differently, and it's what's called long format instead of wide format. So if there are 4 levels of your independent variable, then you're just going to have 4 rows for each subject. And then you'll just have 1 column for your DV. So just slightly different. Want to point it out before we get into the example or into the labs because it causes confusion. So we just simulated data, ran it through R. You're familiar with this example, so I'm just cutting to the chase here. Up at the top, you'll see the AOV command. We're still just doing an ANOVA, so it's AOV. But there's an important difference at the end of the function. So at the beginning, it looks familiar. So we have a data frame called WM for working memory. The DV is IQ, technically IQ gain. And the IV is condition. But since this is a repeated measures design, we have to tell R that we need a special error term. Because remember, the error term is different here. And the way to say that is to tell R that there are subjects across conditions. So the subjects are measured repeatedly across conditions. So that's the error subjects over conditions. There's one extra piece in this example in particular, this won't apply to all examples, is the factor function. If you look back at my data structure, I used numbers for subject ID. So R is going to read that as an integer. We do not want that to happen. We want it to be read as a factor. So we can use the factor function to change that. So that's an extra step in this example. So now let's go to the summary tables. Again, it's just an ANOVA. It's just a one-way ANOVA, so the summary tables, really easy. But it's a little more interesting than a one-way between groups ANOVA because you have the systematic variance due to subjects. And R prints that first. That's here. So remember, we had 20 subjects, so you can check that here. Degrees of freedom is 19. Number of subjects, -1. So I know that this is the summary of variance due to subjects. So that's sort of taken out. And then we go down here to look at our effect of training. That's called condition. Degrees of freedom is 3. That's good because there were 4 levels. Residuals, what's the error term? It's the interaction of A by S. So it's the product of degrees of freedom for subjects times degrees of freedom for conditions. So 19 times 3 gives you 57. And if we look all the way to the end here, we got a nice low p-value, nice high p-value, or nice high f-value, significant effect. We made up the data. We wanted to make it that way. And I didn't print the effect size, but the effect size is the same. You can calculate eta squared. Again, it's just sums of squares for the effect over sums of squares total in this case because it's one way. So if we could sort of do that in our head here, it's almost 200 over 400. It's about 0.5 would be the eta squared. You know, we could run it in R. Just as we did for one-way ANOVA, one-way between groups ANOVA, we now have to follow that up with post hoc tests. And the procedures that are available to you, again, there are many, and they're different from the ones that are used in between groups ANOVA. Why would that be the case? Well, in between groups ANOVA, remember, we get to use a pooled error term, assuming homogeneity variance. But now the whole concept of error has changed here. And error sort of depends on the design, right? Because it's A by S. So you can't use one error term for all your post hoc comparisons. So the procedures that are available to you for post hoc tests in repeated measures ANOVA are all different. It's the same logic. They all just adjust for multiple comparisons so that we don't have this inflation of probability of type 1 error. But you'll see different names for them. So the default procedure in R is interesting because it's not that familiar to me. It's called the home procedure. And there's this nice function called with where we can just print all the pairwise comparisons in one step rather than doing them one by one. So again, we'll cover that in the next lab. But what I've done here is I just specified the data set, said we're doing pairwise t-tests on IQ with condition as the variable, and we set paired to true because this was a repeated measures design. And I don't have an argument about which type of procedure to use, again, because in R the default is home. So here they all are. It does the pairwise comparisons, and those are the p-values. Again, they're significant except for same as the between groups example. The comparison between 8 and 12, not significant, and 17, 19, not significant. But what I want to do is show you how those p-values change ever so slightly as a function of procedure. So here's that most conservative procedure, Bonferroni, that does exist here in repeated measures. Again, we use this nice nifty with function. And it's the same exact thing as I did in the last example, except now because home is the default, I want to change it using the p-adjust method argument. And there are many options. I put in Bonferroni because it's the most conservative. And then here's all the p-values. Just one more, I'm going to throw in just the paired samples t-test because we did this with the one-way between, right? So say we didn't know how to do ANOVAs, right? You didn't know how to do ANOVAs 2 weeks ago. You would just do a bunch of t-tests. If you did that, here's your p-value comparing day 12 to day 7. And here it's paired equals true. So let's compare those. The paired t-test, again, does no adjustment. It exists as if you just did that one test. So it has the lowest p-value. The home procedure is sort of like Tukey's in the between case. It's sort of in between. So it does an adjustment, but it's not as extreme as Bonferroni. Look at Bonferroni. It's almost not significant, right? It's up at 0.04 basically. So again, that's the most conservative. So that would be the range of p-values that you would get using different procedures. And again, they all just differ with respect to how they handle this inflation of type 1 error. So to summarize this segment, repeated measures ANOVAs are appropriate when you're comparing group means, and specifically when you're comparing 3 or more group means that come from the same sample of subjects. And as we covered in this lecture, there are a lot of benefits and a lot of risks involved in repeated measures designs, and you have to weigh those if you're considering doing experimental research and making a decision between a between groups design and a repeated measures design. And because it's an ANOVA, it's going to generate an F-test or F-ratio. That's a null hypothesis significance test, so we can follow that up with effect size. And since it's an F-test, if it's significant, we need to follow it up with post hoc tests, which are a variety of procedures that all protect against that inflation of the probability of type 1 error.